Welcome everyone. In this video, I will be covering section 16.6 Parametric Surfaces and Areas. This is a bit long section. You may have to watch them in different parts. How to parameterize a plane curve and how to parameterize a surface. We have already seen how to parameterize a plane curve um, in, in Calculus 2 and also in chapter 13. Now we'll see one more time. We have already looked at how we can parameterize a plane curve or a space curve using r of t equal to x of t, y of t, which is a plane curve. And r of t is x of t, y of t, z of t in a space curve. We use one parameter t. Here you notice there is only one parameter t we use. For a curve, either it could be plane curve or a space curve, we need one parameter. Whereas to parameterize a surface, we will need two parameters and three dependent variables. R of uv equal to, we write like this, x of uv, x as a function of u and v, the parameters u and v, y in terms of the parameters u and v, z in terms of the parameters u and v. These are the components of the vector r of uv, which represents a surface, where u and v define a region D in the uv plane, and r of uv will sweep out the surface. So as shown here, uv runs over the domain D in this first figure. And in the second figure, you notice that the vector r of uv sweeps out a surface, which is in blue. R of uv is a vector. So the tip of the vector sweeps out the surface. Thus, R of uv written in component form can also be written as a vector in terms of the basis vectors ijk. So you can write R of uv as x of uvi plus y of uvj plus z of uvk. And this is a vector, and it's a vector valued function on the region D in the uv plane. So x, y, and z, the component functions of R, are the functions of the two variables u and v with the domain D. The set of all points x, y, z in R3 such that x as a function of u and v, y as a function of u and v, z as a function of u and v, and uv varies throughout D is called a parametric surface. Parametric surface, yes. And equations too are called uh, the, the parametric equations of S. Parametric equations of yes, the surface yes. So if you notice in this picture, each, each choice of u and v gives a point on S. So each point of uv gives a point on S. By making all choices, we get all of the surface S in blue. So this is the surface. In other words, the surface S is traced out by the tip of the position vector r of uv, as shown in this figure, the pink line in the second figure, r of uv, as uv moves throughout the region D So region D, the point varies here. Then for every point you see a vector, a position vector on the right side of the figure. Then the tip of the vector, traces out the surface. Let's try problem number 5 from this exercise. Identify the surface with a given vector equation r of s of t, r of s comma t equal to, in component form, s cosine t, comma s sine t, comma s. So r of s of t, so this is vector r of s of t. So it is vector given in terms of two parameters. So it represents a surface with the parameters s and t. We are going to identify, is it any familiar surface that we have done earlier? Like, is it a plane, sphere, or any quadric surface, cylinder or cone or anything like that? So that's what we are going to try here in this problem. Let's take this problem here. Identify the surface with the given vector equation. R of s of t is s cosine t, s sine t, s. So this is, the equation is given in parametric, the surface is represented in parametric form. The surface is given in parametric form. The parameters used are s and t. Now, if we write the parametric equations of the surface, we can write x, y, z separately. S is the first component, s cosine t. Y is the second component, s sine t. And then z is the third component, s. So now we have to see what connections can we make in x, y, and z. So because we see cosine t and sine t, and we know Pythagorean identity, so we will see what happens when we write x square plus y square. So it is a square cosine square of t plus a square sine square of t. So if you common factor the s square, you get s square times cosine square t plus sine square t, which is equal to 1 by Pythagorean identity. That's x square plus y square equal to s square. Can we write s differently? So we notice here s is nothing but z. So s square can be written as z square. Yes, x square plus y square equal to z square. So for any point x, y, z on the surface, we get this surface. For any point x, y, z on the surface, yes, we get x square plus y square equal to z square. So as there is no restriction on z, doesn't say it's only positive z or negative z, we know that z square equal to x square plus y square represents a circular cone. Now, do you remember how a circular cone looks like with the z? So this will be the x-axis, this is y, and this is z, and you have a circular cone directed towards the z-axis. So it will be kind of, I'm just drawing the rough picture here. So it will be here on this side. There is one on this side. That's a circular cone directed towards the z-axis, whose axis is the z-axis. Hope this video helped. Now, this is part A of this section, and then you can watch the other sections, other part of this section in the other parts of this concept video. For part B, you will next watch part B of this concept video, concepts in section 16.6.